Hello, everyone. I'm meteorologist Sean Sublette, and welcome to Across the Sky, our national Lee Enterprises weather podcast. Lee Enterprises has print and digital operations in 77 locations across the country, including my home base in Richmond, Virginia. I'm joined this week by my meteorologist colleagues from Across the Sky, Matt Holiner in Chicago and Joe Martucci in Atlantic City and all across the Jersey Shore. Our colleague Kirsten Lang is taking a few weeks off to be with family. And fellas, we've got a fabulous guest this week, our buddy Tony Rice, a NASA ambassador. We go to him for all things about astronomy. We've had all the Aurora talk recently, so we're going to get into that and all things space weather. And space weather is something that it's hard to explain. I mean, it's what's going on in the sun, and then how it affects what's going here on Earth, but it's not weather the way we think of weather. You know what I mean?
Yeah, there's no 7-day forecast that you put out with the high and low temperatures on this stuff. But it's about the interaction of the, proverbial world around us and the worlds around us, right? Jupiter, Mars, Neptune, they all have their own types of weather. In this case, we're talking a lot about the sun and how the sun, and its interaction with the air or lack thereof, whether it's Earth or in outer space, and how it impacts us. So Tony also, we should say, Sean, has been on a number of our podcasts. He has given us the astronomy report, usually towards the end. So we're happy to have him and actually speak to us for more than the 60-second little blurb he has. So we have a whole half hour with him, and I think everyone's going to enjoy it. If you like space, I think most people do. NASA always rates very highly as the government organizations with high favorability ratings. I think you will like this podcast episode. It'll be good.
Yeah, I've really enjoyed Tony's astronomy reports. I always enjoy that segment of the show. He always is coming up with something that's just super interesting, whether it's something to look at in the sky or talking about the auroras. And so we knew that just off those little minute segments that he does, the guy is just fascinating. We got to bring him on, do a whole episode with him, and that's what we did. And sure enough, ended up being a pretty fascinating conversation.
Yeah, we're gonna jump right into it, from auroras to space weather, radio blackouts, all that stuff. Here's our conversation with NASA Ambassador Tony Rice. Our guest this week is Tony Rice, NASA Ambassador, which means does a lot of education and outreach about astronomy and space science. Tony, thanks for taking some time with us on the Across the Sky podcast. It's good talking to you again, man.
Yeah, it's been a little while since we've run into each other. I appreciate the invite.
You bet. Before we get into all the good stuff, auroras, GPS, coronal mass ejections, can you explain to the listeners what a NASA ambassador is?
So it's a volunteer program through NASA's Jet Propulsion Laboratory, and it dates back to the Galileo probe, actually, and was an outreach program that was started on that. It's really expanded a lot. And what we do is just basically try to get people interested in all the cool things that are happening in the sky. And there's ambassadors all over the country. So if you are a meteorologist, a broadcast meteorologist, go on the JPL website and look for NASA ambassadors and reach out to your local ambassador, especially if you're a teacher or a scoutmaster or anybody that's working with formal and informal education. Reach out to your local ambassador, and they can bring some really cool resources in and share some really cool things, not just about astronomy, but about all these cool missions that are happening right now that are teaching us so much about the universe.
There is so much. The auroras have gotten a lot of press recently, and with good reason, and I do want to get into those. But first, I want to step back about the cause of the auroras in the first place. We know Earth has this magnetosphere, and it bends in particles and stuff like that. But I want to go back to the sun first, kind of where the energy is coming from. These come from things called solar flares, coronal mass ejections. Can you tell people what the difference between those two events are?
They're very much related. And when we think about the sun and we take a glance at the sun when it's directly overhead, or especially when we see it down on the horizon at sunset, it looks very static. It just looks like this orange disk. there on the horizon. But the sun is a very, very dynamic thing. It rotates like our planet rotates too. So we're keeping an eye on all this dynamicism that's going on there. You might have heard of sunspots. We probably heard of some solar flares. You mentioned coronal mass ejections. There are all of these things that are going on there that when they reach a peak, when they reach kind of a critical mass, they can create events that are very much going to impact us here on the Earth. So a sunspot is actually a cooler spot on the surface. I'm using the surface very very generously because this is, of course, a boiling hot gases there on the surface of the sun. That cooler spot, all this energy is coming up from the center of the sun. It's got to get its way out, and it makes its way around that cooler spot. And there's a lot of magnetic forces that are happening at the same time on the sun. So it's going to follow those magnetic lines. That energy is strong enough, it can follow those magnetic lines upwards and creates these kind of ropes. Almost looks like twisted rubber bands. And we're talking a scale of several Earths long. Huge scale. And as those ropes continue to twist back on themselves, they can snap. And when that snaps, there's a bunch of energy that is released in something called a coronal mass ejection. And it's going to push the normal amount of solar wind that happens all the time, just that energy and the particles that are being pushed out by the sun, just by it continuing to burn its fuel, it's going to push it out in a much more violent fashion and create some of the effects that I'm sure we're going to talk about here in the next couple of minutes.
Okay, so how is that a little different from a flare?
So that is a flare. Yeah,
so that's the flare.
That's the flare, and a coronal mass ejection is a very significant flare, we'll call it.
Okay, all right, very cool.
Just continue to walk us through the process here, because we have this huge, it's a big pulse of magnetic energy, right, that's coming towards Earth, right? And so the Earth's magnetic field is helping to drive these auroras. But what would happen if the Earth didn't have that magnetic field?
Well, we'd all see auroras. That's one thing. And we'll talk about why the upper latitudes are the ones that see them most often. If the magnetic field didn't exist, we'd all see auroras, but also all of you would be out of a job because we'd have no atmosphere. There'd be no meteorology. We'd be Mars. And that's one of the big things about all the talk we have about going to Mars that sometimes gets glossed over is Mars doesn't have an appreciable atmosphere. It's like 1/100th that of Earth. And the reason it doesn't have an appreciable atmosphere is because it does not have that magnetic field that we have here on Earth. So picture Earth. Now picture a big, Sean will appreciate this because I'm going to use a Southern reference. I think you've got it up there in New Jersey. I don't know if you've been blessed with it yet in Chicago, but picture a giant Krispy Kreme donut. Really big, Earth-sized donut. A couple of those. Okay, you're in good shape then.
Yes.
So picture a giant Krispy Kreme donut surrounding Earth, and we're down in that hole. That is the shape of the magnetosphere, roughly. It's a torus. It's this donut shape, and it's not perfectly shaped because that solar wind actually causes the backside of the donut to stretch outward. But anyway, so as the solar wind is coming in and all that energy, all that magnetism and the charged particles and all of that, it's being deflected away from particularly the lower latitudes. Now, the upper latitudes, that magnetosphere is, as the name suggests, it's magnetic. Those particles can follow those magnetic field lines down into the donut. And as it moves farther down into the donut, that's when we start to see more effects of it, such as the aurora.
So, we had this big aurora event just about, what day was it? I believe it was April 23rd going into the 24th. That Sunday night. And here in New Jersey, we're about 40 degrees latitude, north latitude here. We did actually get to, quote unquote, see the aurora, but many people, I think, were disappointed that they couldn't see it with a naked eye. You can only see it with a long exposure camera, at least in the southern part of the state where I am. Tell us about, in that specific event, how far south could you have seen that aurora, both with and without the naked eye? Because it really captured the attention of the country that Monday.
This was a naked eye event farther up into the upper latitudes. So let me ask you this one question. The pictures that you saw, that long exposure that you saw, was it overhead or was it closer to the horizon.
It was closer to the horizon. It was in Wildwood, New Jersey, which is actually just about 39 degrees north latitude if we're really splitting hairs. But I did actually get a report, Tony, up in the far northwest corner of the state, about 41 degrees latitude, that you could very faintly make it out with the naked eye there. So I'm wondering if that was about what you heard of across, your findings over that day.
The most beautiful pictures I saw were actually taken near Asheville, North Carolina. So visibility was that far south, but again, those were long exposures. Long exposure photography can create some really amazing images. It's worth pointing out that all those beautiful space images that we see, whether it's taken with something like the James Webb Space Telescope or any of the amazing images that we can see taken from the ground, almost all of those are stacked images. They're long exposures, and many of them, dozens, sometimes hundreds of them, stacked on top of each other, because it's just, you see things when a photon of light hits your eye, and there's just not that many photons that are available to you when it's something that far away. I ask about where you saw it in relative to the position in the sky. What you were seeing there in New Jersey was probably directly overhead, much even closer to the Canadian border. These things are happening very high up, even past the stratosphere. So when you see something that low on the horizon, know that you're actually looking quite a bit farther away, and that's the reason it appears so low. Also keep in mind, I mentioned looking at the sun directly overhead, how very bright it is. Now we can look at it when it is sunset, because we're looking through 40, 50, 60, 80 thicknesses of atmosphere there. So when you see it on the horizon, it's so very much dimmer because you're looking through so much more atmosphere. And that's causing those photons not to make it to your eye. They'll make it to your camera lens, and your camera lens can have a whole lot longer exposure than your eye can. So you're really up against the distance there.
And I'll just say too, Tony, that long exposure camera was also taken by a fellow NASA ambassador. His name is Chris Bakley, who's over here in Cape May County. And it was a phenomenal photo he took. But I appreciate the insight into that, because I was curious too.
And that's not something you can walk out with your iPhone and snap a picture of.
Not yet,
Those
right?
kind of images take a lot of practice to do right. It's beyond me. I really lean on a lot of friends that are really into that to get some of those incredible pictures that I share myself on Twitter and other places.
And Tony, with this most recent event, was there anything for us to be concerned about? Of course, you get these wonderful images and everybody gets excited about seeing something they usually don't get to see. But then the other thing that usually is associated with it is the buzzword, a solar storm. So was there any danger to anywhere on the planet with this most recent event? And what kind of a solar storm would we be talking about to really cause disruptions and problems?
Aware, yes. Concern, no. And the word solar storm, it aligns really well with, we'll call it terrestrial meteorology. Y'all are not the only ones making predictions out there. We've got our Space Weather Prediction Center, also run by NOAA, that is watching these kind of things. Nothing to be concerned about there for most folks, but these kind of impacts, when we see the additional auroral activity and see it that far south, the reason it is making that far south is because it's diving deeper into that donut that I was talking about. It has the energy to push further south. And that additional energy does create some additional risk for particularly something like an airline pilot or even the passengers that would be flying in one of those polar routes. I know there's a lot of polar routes that are flown out of Chicago into some of the Chinese destinations and other parts of Asia. Airlines will delay and sometimes even forego a flight that's going polar, that's following a polar route, when there is a solar storm that is predicted because of the increased radiation exposure.
So disruptive for the airlines, what about communication, as far as like GPS communication, satellite communication? Does it interfere? Could there be a solar storm capable of disrupting cell phone signals, for example? What would it take for that to happen? Or is it not possible at all?
Probably not cell phone signals, because most of the impacts are happening in the upper atmosphere. There are two areas. You mentioned one of them. GPS is one. high frequency communications, particularly the ones that the airlines use when they're flying over water, when they don't have towers near them. They will communicate using high frequency radio. It's up to individual planes to report their positions to each other. Some of that's done via satellites as well. GPS signals can be disrupted by solar storms because of what these storms do to the atmosphere. They can make the upper atmosphere denser. They can make it more lumpy. And that's going to introduce errors into the GPS signals that could cause a GPS blackout for a period of time. And we've got to remember that in today's world, GPS isn't just something we use to get to the grocery store in our cars. It's critical to aviation. It's even critical to agriculture. So many of the tractors now are driven by GPS, and they're planning things, and they are they're watering, they're fertilizing based on down to the centimeter level of accuracy. And when that's lost, farmers are parking these tractors for a period of time until the solar storm threat is over.
Yeah, I want to talk more about those when we come back after the break. But before we toss to break, Tony, one other question I wanted just to get out there is about the colors of the aurora. I mean, my understanding is that, you have high energy particles. They're coming into the atmosphere. They slow down, and depending on what the gas is, once they release the energy, it comes out in a photon of light. Is that about right, or is there something a little more accurate about that?
That's a pretty good way to describe it. Another way of thinking about it is we've all seen fireworks, and there's different colors of fireworks. It's different elements that are reacting in the upper atmosphere in the case of the aurora, and that those are the elements that are a part of the atmosphere itself. All the sun is contributing here is the energy and the charged particles, and comparing that to fireworks. The fireworks themselves are made up of different elements, so they burn different colors.
Is green nitrogen or oxygen? I get them mixed up.
I'd have to look it up. I don't know off the top of my
head. That's fine. That's why we have Google. All right. So we're going to take a quick break. And then on the other side, I want to talk more with Tony Rice, our NASA ambassador, about space weather and some of the other issues that space weather presents for life here on Earth. So stay with us. We'll be right back with more on the Across the Sky podcast.
Hey, it's Chris Mitchell. After 10 years with no dog, we got Walter. I bring him to work with me a couple days a week, but on the days when he's not here, he goes to Ridgeside Canine for puppy daycare. Walter absolutely loves it there, and I know he's in great hands. Clean, spacious, happy. We even see pictures on Facebook of what he's up to. I love that you can have him train your dog while your dog's with him. I can't recommend them enough. Ridgeside Canine Training Facility and Aquatic Center on Gateway Drive in Winchester. That's RidgesideCanineWinchester.com.
And welcome back to the Across the Sky podcast. I'm here with NASA Ambassador Tony Rice, talking all things auroras and space weather. One of the great things or resources that we do have, Tony, is the Space Weather Prediction Center. And this is part of NOAA, right? They do all of our terrestrial weather gathering or data gathering. You go to the swpc.noaa.gov site and you see space weather conditions. Okay, this is great. But you see RSG, which is, radio blackouts, solar radiation storms, geomagnetic storms. What's the best way to interpret what those three categories are and what they impact?
And impact is the answer. Each one of those areas has a different impact, or has a different area where the impact is felt the most. So you can have a green condition on R for radio blackouts, and a yellow or red condition on the S component of that, which is solar radiation. They don't want to reuse R for obvious reasons. And that's going to be looked at by somebody like an airline differently. Okay, so there's no radio blackout conditions expected in the next 24 hours. So that's green. So all of my transatlantic flights are probably okay. Their high frequency communications are probably not going to be impacted by anything solar. though the solar radiation readout there is showing a yellow or a red. I might want to rethink some of those over the pole flights that we were talking about earlier. And then the G stands for geomagnetic storming. That's how much of a risk that we might see in the next 24 hours of a geomagnetic storm occurring. Now, when we see that go above a green, that's when we start looking for auroral activity. So some of these things have some positive connotations and some of them have some negative connotation when it comes to the aurora.
All right, so to follow on that, we know that the higher energy storms are going to produce broader auroras, and they do have the potential to do some damage. So I'm sure you're familiar with the term Carrington Event.
Oh yeah, definitely.
Without getting too deep in the weeds, that was a very, very, very bad solar storm that took out power grids in the late 19th century, I think it was, or early 20th century. I forget exactly when. So here's the thing for those of us who study disasters. Is that something we should really worry about? Is that something we should kind of have in the back of our minds? There's so much stuff to worry about nowadays. How much do we need to think about solar storms and electrical grids in this day and age?
Now, anybody listening to this podcast probably doesn't need to worry about it. Again, awareness, not concern. But right now, go to your pile of bills and go look for the power bill. Get that name of that power company. That power company has somebody sitting in it right now, or maybe their parent company, or somebody is overlooking their power grid. Is probably sitting in a mission control type room with lots of really pretty maps up on the wall, with projectors showing them, and probably one of those maps is coming from the Space Weather Prediction Center. And there may be another image of the sun that's coming from one of the NASA assets, and we can talk about. I'd like to talk about it. Some of the instrumentation is out there that helps us do these predictions. They are worrying about this, and they are very interested in the kind of forecast that the Space Weather Prediction Center is putting out so that they can get ahead of any solar storms that are coming that might create a Carrington event. Now, I wouldn't worry so much about a Carrington event. These kind of events are very much like floods. They're very much like hurricanes. They come in different strengths, and there's 100 years events, there's 1,000 years events, that kind of thing. It's all about risk and probability. So you mentioned the Carrington event. That's probably the biggest one that we have on the books. Do you know that there was a power grid failed back in 1989 because of a solar storm? Hydro-Quebec, their power grid, which serves both Ontario and upstate New York and some other areas as well, it went offline because of a solar storm. Now, we've got a lot more assets up there in space that help us watch for these things. We've got things like the Space Weather Prediction Center that NOAA runs. There's a space weather group at Natural Resources Canada that's keeping an eye on these things. So, long-winded answer, you don't need to worry about it because there are people that are definitely on top of this.
Okay, so that makes me feel better. But yeah, do tell me a little bit about what we have up there in orbit to monitor. I mean, I've heard of SOHO, I've heard of a couple other things, but what other craft do we have up there to monitor what's going on the sun?
So it kind of comes down to two measurement techniques. It's really not that different from anything else in meteorology or a lot of other science. There's observation, and then there's in situ measurements. It's actually measuring the solar wind and its components as it passes that spacecraft. So we do monitor the sun from the ground using optical instruments and watch it for things like counts of sunspots. That's where these things happen, so we want to stay on top of that. And we do watch it with a couple of NASA assets, specifically SOHO and Stereo, which are there looking at the sun 100% of the time. SOHO in particular is really interesting because it has a camera on board that creates what they call an artificial eclipse. It is covering up the brightest part of the sun at all times so that it can watch the atmosphere around the sun, called the corona. And that's where we see things happen. That's where we see these coronal mass ejections as they occur. We see changes in magnetic fields around the sun. But the instruments aboard the Solar Heliophysics Observatory are really, really important because they don't eclipse the sun. They are looking directly at it. And those are the ones that we really want to see, those kind of CMEs, those coronal max ejections, because those look like, they call them crown events, they call them halo events, because you see this circle of influence as this ball of energy gets pushed out. And what you're seeing is it's coming right at us. Those are the really, really important ones. Those are the ones that are going to possibly impact Earth. Because these CMEs, they can happen anywhere on the sun. And keep in mind, this is all happening in 3 dimensions. So some of those CMEs might be directed directly up, not in Earth's path, but it's those ones that are directed directly at us that are a problem. So I mentioned some of those in situ measurements. There's really 2 instruments out there, 2 spacecraft that we use to measure those things. One is ACE, and it is all about the solar wind. It's measuring various components of the solar wind, the density of it, the temperature, the polarity. The polarity of the magnetism at that point can impact how deeply that energy is going to make it into that donut that we've been talking about. But the really important one is DISCOVER, and that's a joint NASA-NOAA mission. It's located out at L1. So there's a couple of Lagrange points. They're points of balance. Really great place to put a spacecraft because it's the point of balance of gravity between the sun and the Earth. L1 is where DISCOVER is. It's between the Earth and the sun. And we've also got the James Webb Space Telescope is out at one of the other L points. We can kind of think of these like buoys, buoys out in the ocean that are waiting for that solar wind to pass over. And until that solar wind or CME or all those charged particles that the sun has spit out wash over that DISCOVER spacecraft, we really don't have a super good idea of what is about to hit us, and can't really make really pinpoint predictions or descriptions of what that is made up of, again, until it passes over that. So less than a day's warning is a way to look at it too, because it's about 1 million miles out, which is not a whole lot when you're talking the distance between the Earth and the sun.
Real quick, before I toss it to Matt, let him go. So if we can detect one on the sun, at least we see something's out there. Then it has to pass the Lagrange point, and then we have the final warning. But how fast is the solar wind going when we have one of these CMEs? Is it, I mean, it's not light speed, obviously.
They vary.
Is it,
they
is
vary.
it a couple of days? I mean, what is the variance in the speeds of these things?
The fastest ones can make it to Earth in about 15 hours, and the slower ones 4 or 5 days. And that's part of what is, it's one of the components of the predictions, based on what we're seeing during that event optically through SOHO or stereo or SDO.
And Tony, you mentioned the word eclipse, and immediately in my mind, I'm thinking the next total solar eclipse next year, next April. I happened to see the one in 2017. I got in the path of totality, and it was absolutely incredible. It's one of those moments that I'll just never forget. It is literally one of those jaw-dropping moments.
You can't overstate it.
It was truly amazing. And so I definitely want to check out the next one, because I want to repeat that feeling and that moment of awe. So what can you tell us about next year's total solar eclipse?
Well, I think that's a whole show right there. We should come back and talk about that, because I've got some tips and tricks from folks that go out to see every one of these, because it is very dependent on the weather, on what kind of experience or what experience you're going to have at all. So we got 2 coming up, actually. We got one in October, and that is going to be an annular solar eclipse. There was just an annular eclipse a week or 2 ago that was visible down in Australia. And annular eclipses occur when the moon is just far enough away that it can't completely cover the sun. So you're left with a ring of fire around. That annular eclipse is going to run from Oregon down through Texas. Now, when you're thinking of will be April of 2024, that's going to run through Mexico, enter Texas, go up through kind of the Ohio Valley, and then out through the Canadian Maritimes. So we can have a whole long discussion about that. It is impossible to overstate how cool a total solar eclipse is.
I totally agree with you there. And I think, yes, we're going to have a follow-up episode as we get closer with lots of tips and tricks for how to take advantage of it. And maybe also how to deal with the traffic, because that was also an issue with the last one. It was incredible traffic.
Get there early, plan to stay late. That is really the only advice.
So yeah, I think we'll have another episode as we get closer to that event. Joe, what do you have?
Yeah, so it's not so much about eclipses, but I'll keep it on the sun here. So I saw that we have an increase in solar activity. We'll continue to see that through 2025. What does that mean in terms of auroras or anything for Earth in general?
We're probably going to see more auroras and farther south. Not only is there an increase in activity, the storms are getting more energetic. So they're punching further south into that donut, which makes them visible further south. So the event we saw a couple of weeks ago that was described as, I forget off the top of my head, I want to say it was a 100-year event. You know how that works with floods.
Yes.
Just because it's a 100-year event doesn't mean it's not going to happen for another 100 years. We're seeing these things happen more frequently. The sun runs on an 11-year cycle. It's called the solar cycle. And we see an ebb and flow of the number of CMEs. It's counted based on sunspots. We're seeing more sunspots than we expected for this point in the solar cycle. We're coming off of a solar minimum a couple of years ago, and it'll be a little while before we reach that solar maximum, where we see the maximum number of sunspots across the surface of the sun. But like I say, it's outperforming. We're seeing more sunspots than we expect. What that means in the big picture of things, that's for heliophysicists a whole lot smarter than me, and they are absolutely studying these things. I'm seeing the papers come through fast and furious. It's something that's definitely worth keeping an eye on for many of the reasons that we've talked about today, the impact that space weather can have on us.
Very cool. And then I think I got the last question here. So I want to circle back to what would happen if Earth didn't have this magnetic field, and you were talking about Mars. And I'm wondering, in regards to developing Mars, colonizing Mars, what can be done? We don't talk about how much money it'll take, but what could be done to actually make Mars habitable in regards to them not having any kind of real magnetic field?
Yeah, I've seen a lot of proposals thrown out there, everything from, bringing the atmosphere with us to purposely creating a greenhouse effect by releasing a nuclear weapon and punching a bunch of dust up into the atmosphere. I think, this is me speaking, I think the thing that makes the most sense to me is probably going underground. It's probably using the soil itself as that tool for blocking the radiation. Standing here on Earth, everybody, whether you're taking a flight to London or you're just working at home like all of us have done for the past what seems like decade, we're getting the equivalent of a chest x-ray about every 20 days. That's 10 times more just on a normal air flight. If you ignore the Space Weather Prediction Center's warnings during one of these events and you do fly over the poles, that's 100 times. It's many, many, many times worse than that on the surface of Mars, again, because of that lack of a magnetosphere. So the lack of an atmosphere is a problem unto itself, but that lack of a magnetosphere is something that's going to have to be addressed. You just can't stay there very long without succumbing to some sort of radiation sickness.
Very cool. I did not know that. Well, appreciate the info.
Tony, anything else you wanted to share before we close up shop this week, man?
So you mentioned the Space Weather Prediction Center, and I really encourage everybody to go out and take a look at that. It's swpc.noaa.gov. The homepage, you're going to see some of those letters that Sean mentioned there. Your first click needs to be dashboards. And the one that is going to give you information about, if you hear that there's Aurora coming, click on that Aurora dashboard and you'll see the maps that show the prediction. And it's this big green blob, and it's the prediction over the next couple of hours of when Aurora might be seen. Note that red line there, the red line that is beneath that green blob, that is your horizon line. If you're above that red line, look to your northern horizon, you might be able to see it. Some of the other dashboards that are there that are worth looking at are the Space Weather Enthusiast. That's kind of got a bunch of different readouts from some of these satellites we talked about, but click on some of the others: emergency management, aviation, electrical power, global positioning. This will give you an idea for how these things are being looked at, and what the impacts are to these various areas. What the electrical power dashboard is probably on the wall in that mission control in your local power company that I mentioned earlier. So it's a great resource. There's some media and resources. There's some videos that NOAA has created that talk more about this and educate more about the different components of space weather.
Tony, thanks so much, man. Where can people find you on social media and to learn more about the stuff you do?
So I'm RTP Hokie, Hokie. I'm a proud Virginia Tech alum. I wear it very well. So I'm RTP Hokie on Twitter. And you can also reach out to me through JPL, through the Solar System Ambassadors website there. And if there's any broadcast meteorologists listening, I love to get in touch with you guys and visit with you and try to get some of this information out so that you can spread it out to your communities as well.
It is always good to let people know what's up in the sky. That's kind of our mantra here as well. Tony, thanks so much for joining us. We are absolutely going to have you back in front of the 2024 solar eclipse, because I'm going to go see it. I just don't know where yet.
Texas.
That's what I'm thinking, because I don't want to be a place that's going to be climatologically cloudy. So that's my concern for sure.
I thought we all said we were staying at Matt's mom's house in San Antonio.
Yeah, San Antonio.
Can we agree on that?
Yeah, I might have to make a trip back home. We might have to clear out some extra space and make room for a few other people.
All right, we're going to let Tony go, and we'll be back with a few more closing thoughts on our Across the Sky podcast.
Looking beyond the atmosphere, here's Tony Rice with your Astronomy Outlook.
NOAA Space Weather Prediction Center forecasted another moderate geomagnetic storm this past Sunday evening. You might have noticed that these tend to be coming a little more often, prompting many to wonder what's going on. It's a very natural upswing that we see every solar cycle. A solar cycle is an 11-year ebb and flow of activity on the sun. It's measured by a count of sunspots. Sunspots are cool spots on the sun's surface that all that energy coming out of the core must route around, and this creates some stress on the magnetic fields, causing filaments and prominences many times longer than the Earth is wide to either fall back onto the solar surface and be reabsorbed, or sometimes break, causing coronal mass ejections, or CMEs. The last solar minimum was in late 2020 when nary a sunspot was visible, ending solar cycle 24 and beginning the current solar cycle of 25. It's not a puff of white smoke that announces the next solar cycle, but a flip of the sun's magnetic fields. The sun's north and south poles switch. Over the next 5 years or so, activity increases until solar maximum is reached. Along the way, you'll see more coronal mass ejections, solar flares, and all that other space weather that the SWPC keeps an eye on. Though most of the spacecraft and methodologies used to drive those forecasts are relatively new, the technology to monitor those sunspots has been around a long time. And when you look across the 400 years of records that are available, there are cycles that appear within those cycles. Solar maximums have tended to get more maximum for a couple of solar cycles, and then less so for a few more solar cycles. Interestingly, they also tend to vacillate between big solar maximums and then smaller solar maximums. Keep in mind that these are separated by 11 years. The patterns provide sufficient information to build forecasts of when the next maximum might be, and how many sunspots might be there, therefore how great a risk of geomagnetic storms. But back to those recent increases. Yes, they are somewhat expected, but the sunspot count is also outperforming those forecasts by a significant amount. This suggests that the trend will not only continue upward, but that our next solar maximum will be even more maximum after a trend downward since solar cycle 22 back in the 90s. You can play with this data for yourself, going back to 1749 on NOAA's Space Weather Prediction Center website. Click on Products and Data, and then Solar Cycle Progression. That's your Astronomy Outlook. Follow me at RTP Hokie for more spacey stuff like this.
And we're back with a few closing thoughts on our discussion with Tony Rice, NASA ambassador on the Across the Sky podcast. And, fellas, I've always trying to make sense of the space weather prediction site. So I'm glad he took some time to walk us through that, because intuitively, I get the idea. Something is belching off the sun. It gets to Earth. It hits the magnetic field. But to understand what the true impacts are, whether it's radio communications, whether it's the electric field, the electric, how we generate and move electricity around here on the ground, all those things are complicated. But I was also happy to understand or to know that there's always somebody looking at that. So I don't have to worry about my electrical grid getting fried.
Well, yeah, Tony said not to worry, but I got to be honest, listening to him talk about that stuff, and it's like, oh, don't worry, other people are worrying about it. It's like, well, that kind of still makes me worry about it a little bit. And how he talked about, not only the flights having to, be redirected away from the poles during these events, but how it could potentially disrupt GPS and how we've become so reliant on GPS in this day and age. And then you go to the next step beyond that and thinking the power grid. When you hear that, when you hear issues with the power grid, everybody just starts to get a little bit nervous. So I really hope, not only are people watching this and forecasting it, but preventative measures are being done in case one of these big ones hits, that we're going to be prepared for it. I hope that's in motion.
Yeah,
and those plans are there.
I mentioned the term Carrington Event in the podcast, and for those not familiar with it, because it is a little bit out there, and I pulled this up from space.com. The Carrington Event was a large solar storm that took place at the beginning of September 1859, a few months before the solar max of 1860. And in August of 1859, astronomers around the world watched with fascination as the sunspots on the solar disk grew. Among them was Richard Carrington, an amateur sky watcher in London. And according to space.com here, on September 1st, as Carrington was sketching the sunspots, he was blinded by a sudden flash of light. Carrington described it as a white light flare, according to NASA spaceflight. The whole thing lasted about 5 minutes. That was basically a coronal mass ejection. So yeah, it could be bad.
Well, do you guys ever get freaked out about it, like how small the Earth is in comparison with the sun? Like we are just such a tiny, tiny blue dot, as we say. But I went to a couple weeks ago, went to Liberty Science Center in Jersey City, New Jersey. Great place. And we went to the planetarium, which I believe is the largest on the East Coast. Either way, it was a video about the weather on different planets, and it kind of swings you around. And when they show the animation of the Earth with like the sun as a big behemoth behind it, and you see that coronal mass ejection flaring out of the sun, I know it's a little, not drawn the scale, but the point is, these things, anything that's coming out of the sun towards Earth is huge, and we have these little tiny instruments trying to detect it. So it just, sometimes I get a little, overwhelmed. I'm like, geez, like we are really on some delicate ground here that we're managing to, stay alive as a planet with the Earth, with the sun just so large in comparison to us. It's quite incredible.
Yeah, so glad to have that magnetosphere protecting us, and thankful for an atmosphere as well, because that's the whole thing. Everybody's like, yeah, we'll just move to Mars. And it's like, it's going to be a little more difficult than you think, because the presence of the atmosphere on Earth, does so much for us. And the lack of the atmosphere on Mars makes it, there's a reason why we haven't found life on Mars yet. It's a lot harder to get by without atmosphere. So very thankful that everything came together, and we're in a lot better shape here on Earth.
Yes,
we're going to live under Mars.
What's that do?
Oh, no, I said we're going to live under Mars, according to Tony.
That's probably the way it's going to have to be done in terms of shielding from radiation. But with that, we're going to go ahead and take a break for this week. We want to say thanks again to Tony for joining us. We've got some great shows in the pipeline, looking at tropical cyclones in the Mediterranean. We're going to be looking at billion-dollar disasters and the like. Those are all coming in the next few weeks. But for right now, for Joe Martucci, as well as for Matt Holiner, I'm meteorologist Sean Sublette. Thanks for listening to the Across the Sky podcast, and we'll talk to you next week.
Michael J. for Hope for the Warriors. Started back in '06 at Camp Lejeune. Military families witnessing the effects of war on their loved ones. Now, almost 20 years later, they've aided over 53,000 service members, veterans, and families with confidential, high-quality behavioral health care services at little or no cost to post-9/11 vets and their families. Over 91% of every dollar donated goes directly to the programs. If you're as concerned about our heroes as I am, go to hopeforthewarriors.org.